Hello everyone, and welcome to this video. In the last video, we looked at different types of control systems, the advantages and disadvantages for some of them, and then we went on to start looking at several systems, what they were, and what they are used for, and we looked at some examples of several systems. Then we we said we will continue in this video to begin to look at the mathematical modeling of several systems. All right, and these same principles you could apply them to any other control system, even if they are not several systems in nature. Okay. Um, so the first thing we want to do is to look at the concept of mathematical models. All right. There are different kinds of models. You have graphical models, you have physical models, right? Which are what we sometimes refer to as prototypes. And then you have mathematical models. The whole idea of modeling is that you represent a real life object, a real life situation, a real life system in a new space, if you like. Okay, so you want to represent something graphically, you generate or you produce graphical models, visual models, models that represent the real life thing, but allow you to see them, right? In mathematics, or yeah, in engineering and mathematics, we can represent the way systems behave, okay, by deriving mathematical expressions or equations that relate the various variables, okay, the various parameters involved in the behavior of that system. Okay, so we have defined mathematical models as the set of equations, mathematical equations, and these are usually differential equations. Okay, that describe the dynamic characteristics of that system. That's what we call the model of the system. So when we want to model several systems, we want to get a series of equations, a set of equations that will describe the dynamic characteristics of the several system. Okay, and there are two major parts of the servo system that we could model. The mechanical aspect of it, mechanical systems, and those systems will have to do with motion, right? And then all the properties of motion, or the yeah, the elements of the characteristics of motion. You'll be thinking about speed, you'll be thinking about acceleration, you thinking about position, all right? And so on and so forth. And then you have electronic systems. So what you're dealing with, this is the control aspect, electrical networks or circuits. You could have electromechanical systems where you have a hybrid between electrical and mechanical systems. So final mechanical systems, we'll look at mechanical translational systems, systems that um, produce translational motion. All right, motion in which rigid bodies, rigid parts move from one place to another in such a way that the orientation of the particles of that rigid body at the beginning of the motion is the same as at the end. Okay, and then you have mechanical rotational systems where you have bodies that undergo some form of rotation. Okay, and generally you will find that you have a combination of both mechanical, I mean, both translation and rotational motion. And then we look at try to model gear trains, okay, because sometimes you will need some meshing of gears as part of your transmission system to either increase or decrease the speed or torque, right? And then for electronic systems, we'll look at modeling of electrical networks, electromechanical systems. I will try as much as possible to be faster today, so that we can cover more ground. I will just handle just the introductory part. Then in the next video, we'll go into Laplace transforms, or Laplace. It's a French name. And then we go on to look at how all of that affects the modeling. Right. Now, but it's critical to note that the mathematical models we are going to derive primarily are in the time domain, right? They are differential equations that you find the derivative of certain properties with respect to time. Okay. But for the majority of what we'll be dealing with, we will be looking at transfer functions. Okay, transfer functions. We want to know in this control system, what is that single equation, if you like, that acts upon the input to give you the output. All right. And so we want to take a small detour and look at transfer functions very briefly, and then we'll come back to this mathematical model. Because what we're going to end up with at the end of the day in the mathematical functions the um, is the transfer functions of these systems. That's what we're going to derive, right? The transfer function of mechanical translational systems, the transfer function of rotational systems, gear trains, transfer function of these systems, not just their differential equations. Okay. And so because it is the transfer function that we are really interested in, it's important for us to understand what um, transfer functions are. Now, when we introduced control systems to you guys, we defined them as systems that would take an input, which is sometimes called the reference input or the desired output, what we desire to see in that system. And the control system would then use that value to work on the system it's controlling in order to give you the desired output. In a simple form, you have the input going into the control system, and something is within that control system that acts on the input to give you the output, right? This is a very simplistic way to describe it. Of course, we know that in between you have actuators that have that physical interaction with the system, all right, to cause it to change that particular parameter that we are interested in. Okay. So when we define the transfer function of a system, we define it as the ratio of the Laplace transform of the output variable, okay, to the Laplace transform of the input variable of that system. And the assumption is that all initial conditions are 0. Okay, so because we are dealing with transfer functions, okay, and I've underlined Laplace transform for you to highlight that the ratio we're dealing with is not the ratio of just the output variable to the input variable. It's the ratio of the the Laplace transform of the output variable to the Laplace transform of the input variable, right? And so it's important to know, of course, at this level, we assume that all the previous knowledge you are expected to have is that you would have done Laplace transforms, you would have done partial fractions and all of that. And when we get to this class, we will just apply. All right. So we are dealing with the ratio of the Laplace transform of the output variable. So this variable here will take its Laplace transform, right? This variable here will take its Laplace transform, and we'll find the ratio between the two, the output to the input. That's what will give you the transfer function. So the transfer function represents the relationship that describes the dynamics of that system. Okay, it tells us what happens to the input that comes into that system to give us the output. Okay, it is an input-output description of the behavior of the system. So consequently, it does not necessarily include any information about the internal structure of the system or how it behaves. It's just giving us a relationship between the output and the input of that system. All right, so what we're looking at, the transfer function, what it gives us is a description of the relationship between the inputs and the outputs. Okay, and that indicates will be an indication of the behavior of the system, not the internal structure of the system. So it's important to note that transfer functions may only be defined for systems that are linear and time invariant. You know, we when we're looking at various kinds of control systems, we did look at one of the classifications where you could classify a control system as either a linear time invariant system or a linear time variant system. It could also be non-linear. Okay, and we define linear systems as systems that fulfill two properties. They possess two properties at the same time. They must have those two properties to be linear. If one of those properties is absent, then the system cannot be linear. Okay, the property of superposition and homogeneity. And we did some examples to demonstrate how you recognize systems that are linear in time invariant. In time invariant, it means that their parameters are constant. They are not changing with time. Okay, the parameters they are dealing with are stationary. So transfer functions are possible only with linear time invariant systems. So sometimes when we find systems that are not linear, we first need to linearize them. So we'll be looking at techniques of linearization at some point within this course, right? So what you work on to get the transfer function is the linearized differential equation of that system. The differential equation is the mathematical model of the system, okay? The mathematical expression that describes what happens to the inputs that gives us the outputs, okay, of that control system. Yes. So we did talk about transfer functions being the Laplace transform. So very quickly, let's jump again and look at Laplace transforms just to have an understanding. Okay. Now, your differential equations, as I said earlier, they are in the time domain. They are functions of time. Okay, that's why you sorry about that. That's why you see that this uh, this expression here, f of t, says that this function is a function of time. Time is the independent variable that whatever else you're dealing with depends on. Is that okay? So differential equations are in the time domain. Now, this time domain, they have certain characteristics, they have certain ways that you can handle them and ways that you do not handle them. All right. You probably would have dealt with both ordinary differential equations and partial differential equations, and you'd have gone through the various ways of solving these two different types of differential equations, right? Now, what Laplace does is it transforms, okay? It takes your equations from the time domain and transforms them to the S domain, what we call the S domain. So your mathematical expression ceases to be a function of time. It becomes a function of the variable x. That's how we call it, the S domain. I'm not going to go into the details of all of that. I will come back. I'll just brush it a little bit later, but I wanted you to understand. The reason why we do this is because the differential equations are sometimes very difficult to solve. But when you transform them, okay, it becomes easy to to carry out basic algebraic operations on those equations. Okay, so you see my footnote that says Laplace transform the yield algebraic equations that are relatively easier to solve compared to differential equations. Okay, so if by the time we start looking at the block diagrams, we've defined what block diagrams are already that represent, the transfer functions and all of that. You see how easy it is to manipulate, okay, your system using basic algebraic operations, and that's only possible when those models, those mathematical expressions and equations are in the S domain. Okay, so what the Laplace transform does is to take your expression, your equation in the time domain and transform it. Okay, it will teleport it from that domain to another domain where you can handle it better. All right, it's just like in mechanical fabrication and all of that. Okay, when you want to mold something made of metal, in the solid state in that domain, you cannot easily force it to take certain shapes and forms. And so you transform it into a different domain. You supply heat, right, that changes the same metal, or it takes it from the solid state to the liquid state, where it's now easier to manipulate its form and shape. Okay? And when that finishes, you take it back to the solid state by cooling. Okay? Just a brief representation of what happens with it. So the S domain offers us ease in manipulating our system than the time domain does. And so we carry out Laplace transforms to bring our equations into the S domain. Then we can easily manage them, solve them, do all the manipulations we need to do, and then we take them back to the time domain. So you will need to go and brush up on your knowledge of Laplace transforms. What I will do, I'll just um, go over the basics, show you the table, and as we do examples, see how we get to transform the expressions from the time domain to the Laplace or the S domain. So let's go back to the transfer function. So we have a system, all right, and there is an input RT. That's the reference input, okay, the reference signal. That's the signal that your system is going to use to determine what the output should be, and that's why we're calling it R of t. Okay, and the first block diagram there is the block diagram for I mean in the time domain. That's why you see R is a function of time, right? And then you have the system, the control system that works on that input and gives us the controlled output. That's why we're calling it C of t. All of that in the time domain, right? Now we can take these various parts of your control system and um, transform them into the S domain, just the way we've done here, right? So um, R of t becomes capital R of S. So usually we would express our mathematical equations using small letters, okay, when they are functions of time. When you transform them or transpose them into the S domain, they become capital, okay? So R of t becomes R of S, okay? This is now in the S domain, and we got R of S by taking the Laplace transform of R of t, okay? Your controlled output, C of t, becomes capital C of S. And then there is something here representing the system that will takes action on the input to give you your output, and we call that G of S. All right, G of S. Okay. So this means when you look at this, the simple algebraic operation here, now that it is in the S domain, is that you input signal, the reference input signal R of S, multiplies your transfer function. Okay, G of S, I was trying to avoid that, but G of S is actually your transfer function. Okay, it's the one that describes the relationship between the output and the input. It's the one that describes the expression that works on the input to give us the output. So you see that the output C of S is, okay, the product of the input signal and the transfer function. All right. And by basic division, basic algebraic division, if we divide both sides by R of S, right, then R of S disappears from this side and then this becomes G of S. That's a transfer function. And then it is C of S over R of S. That's where our definition of the transfer function came from. Is the ratio of the Laplace transform of the output variable to the Laplace transform of the input variable. Okay, now this is an open loop system. Okay, when we're looking at the types of systems, we looked at one of the classifications where you could classify control systems as either open loop or closed loop systems. Now, this is an open loop system because nothing of the output is being fed back to the input to check, whether the desired input is being achieved. No, the input just comes in, the system works on it, and whatever output comes out, you take it, whether you like it or not, right? It's an open control system. Input, system, output. This is a transfer function for that. Now, when we now begin to look at closed loop systems, one of the things that makes closed loop system possible is the comparator or the error detector. Okay, we defined all of this in the last video. So what the error detector does is it compares two signals. All right, and you could have a positive comparator, you could have a negative comparator. Okay, so what the comparator does is very simple. You have, in this case, signal A coming in, and it's coming in on the plus side. That means we are adding it, right? You have signal B also coming in on the plus side. This is a positive comparator, plus, plus. So the output of the comparator is a summation of the two inputs coming into the comparator. So it's A plus B. When it is when it's a negative comparator, you see that A comes in as positive, right? And B comes in as negative. And what we're doing is we're taking B out of A. We're checking what's the difference, what's the error. We expect these two values to be the same. Now, by how much do they differ? Okay, so the output from this negative comparator is A minus B. All right. This kind of simple operation is possible when you are in the Laplace domain. You are in the S domain. It's not as straightforward in the time domain. Okay. And that's why we always do the transform in order to get to have this possible. Okay. So we've already said that this is a transfer function of an open loop system. Okay. Your input reference signal is that. It's in the S domain already. This is your output signal. And that is your transfer function expressed like so, right? Now, how about a closed loop system? Now, let's look at this very, very carefully. Okay, this is a closed loop system, right? And this is the block diagram for a very simple closed loop system. You have your reference signal coming in. There is a comparator that checks with the output signal, all right? Portion of the output signal or the feedback signal, okay? Now, the difference between these two gives us the error signal. Because of this negative, this whole closed loop system is called the negative feedback system, okay? We're feeding the output back. This is called the feedback, right? To the input for the purposes of comparing. Okay. So this is your signal A of S. This is your feedback signal B of S. And this is your forward loop transfer signal, transfer function, I beg your pardon, G of S. This is your feedback transfer function, H of S, right? And then your output is C of S. Okay, so if we move from left to right, the reference signal comes to the error indicator or the comparator. The feedback signal also comes in. There is a comparison. The output is your error signal that goes to your control system, right? The transfer function of your control system. Now, this will take the error signal and work on it to give us the output signal. Now, a portion of that is taken to your feedback transfer function, right? And then that um, gives us your feedback signal that goes back and the loop continues. Is that okay? Now, so let's look at these mathematically using basic algebraic operations. E of s is the output from the comparator, right? E of s. Now, because that's positive, your R of s coming into the comparator is coming in with a positive sign, but your B of s coming in is negative. So your E of s, the output, is the difference between these two as we've expressed in equation 1. So the error signal is the reference signal minus the feedback signal, right? Then, when you look at the output C of S here, okay, what is coming into this transfer function is E of S. So the output C of S is a product. G of S acts on E of S to give us C of S. And that's what we have here in equation 2. C of S is G of S, the transfer function, times E of S. Okay, the error signal. Then your feedback signal B of S is the output from the feedback transfer function. Right? What comes into your H of S is C of S. Okay, so we can say that B of S is a product of this transfer function H of S and the input signal coming to it, which is C of S, as is expressed in equation 3. Okay, now in this closed loop system, there is an equivalent open loop transfer function. Okay, so there is an equivalent open loop transfer function. And that open loop transfer function is, so assuming that R of S comes in here and there's no comparator, R of S comes here, it goes to E of S. E of S is actually the input here. So E of S comes to G of S and it also comes there into H of S and out to B of S. So B of S is our output, E of S is our input. So we define the open loop transfer function of a closed loop as the ratio between the feedback signal and the error signal. From equation 3 tells us that, where's my equation 3? Equation 3 says that B of S is H of S and C of S, right? But we know what C of S is in equation 2. So we take the value of C of S in equation 2 and substitute. Obviously, as we inspect, you'll see that there is an error signal there. And since I want the ratio between the feedback signal and the error signal, that's what to pick up, right? So I pick equation 2, C of S, substitute that in equation 3, okay? So that's what we have here. So instead of C of S, what we have is G of S, E of S, because the output C of S is a product of a G of S, the forward loop transfer function, and the error signal. Okay, so if we now divide both sides of this equation by E of S, on the right hand side, it will cancel itself out, leaving you with H of S, G of S, or G of S, H of S. Okay, we've ordered it this way because that's the order that you meet as you move from left to right in this way. Okay, you see G of S, then H of S, right? And then on this left hand side, you now have B of S over E of S, which gives you the open loop transfer function of this closed loop system. Okay. Then to find the closed loop transfer function, if we should go back to these equations here, the closed loop transfer function, which is actually the overall transfer function of this closed loop system, is going to be your output signal C of S, that's the controlled variable, right, to the reference variable R of S. So what we want to do is we want to find an expression that gives us that ratio C of S over R of S. Now, when you look at this equation, equation 2 has C of S here, right? C of S equals G of S times E of S, right? But equation 1 has what E of S is. So what we're going to do, and when you look there, there is our R of S, which we need to actually define that closed loop transfer function. So we're going to substitute the value of E of S, which is R of S minus B of S, in equation 2. All right? So that's what we're going to do. So when we jump there now, we're saying equation 2 says that the control variable C of S is given by this expression. Okay? But we know that our E of S is this guy here. Okay? R of S minus B of S. So we'll bring it in here. This is a bracket, right? So we are going to open this bracket. That means that the coefficient of this bracket is going to open multiply every term in the bracket. So C of S equals G of S times R of S. That's the first term there. And then G of S again times B of S. That's your second term. Okay? But we know what B of S is, right? The feedback loop. Okay? That's if you look at equation, where are you? Equation 3. Equation 3 tells us that B of S is H of S times C of S. And so, but B of S is this guy. So wherever we see B of S, we will substitute this value in its place. Okay? So let's follow this guy now. So C of S is the product of your for loop transfer function times the reference signal minus G of S for loop transfer function times. Now, instead of our feedback signal, we now have these two products. Okay? H of S, C of S. Now, when you look on both sides of the equation, there is a C of S here, there is a C of S here. Okay? We want them to be together. So we're going to add this whole expression here, G of S, H of S, C of S, to both sides of the equation. Or we say we move this expression to the other side of the equation. And when that happens, this becomes positive on this side. So we now have C of S plus, okay, this has crossed over the equals sign, plus G of S, H of S, C of S, that's the expression, equals what's left on this side. We've taken this away. All that is left is G of S, R of S, okay, which is this here, G of S, R of S, right? Now, we can come back to the left-hand side and factorize C of S out. The C of S here, the C of S here, okay? If we factorize out, okay, C of S comes out of that bracket, we create a bracket. C of S is the only term here, it's the only function there. So when you factorize it, our what will be left to be 1, okay? And when you factorize C of S out of this product, what you have left, this simply just vanishes away. What you have left is these two guys here, G of S times H of S, right? On the left-hand side. Then on the right-hand side, we have G of S times R of S, as we did have before. So what we're looking for is the ratio of the output, the Laplace transform of the output variable to the Laplace transform of the input variable, that is C of S divided by R of S. So simple, division. Okay, we divide both sides by R of S, and at the same time divide both sides by this whole expression here, 1 plus G of S times H of S. Okay, so R of S will come down here, 1 plus G of S, H of S will come down here. So on the right hand side, what you have will be G of S all over this guy. On the left hand side, you'll be C of S all over R of S. Okay, and that is what we now have here. When we divide both sides by R of S and 1 plus G of S, H of S. Okay, so C of S over R of S equals this expression here. Okay, so this is the transfer function of a closed loop system. And note this, because this is very intuitive, that this is for a negative feedback system. So whenever you have this here, okay, where your comparator is a negative comparator. It's subtracting your feedback signal from your reference signal. Then your expression here, this sign here will be positive. So you just alternate. If this is negative, this is positive. All right. And this is also very intuitive that your forward loop transfer function, it stays as the numerator of the closed loop transfer function. Then your denominator will be a product of your forward loop transfer function and the feedback transfer function added to 1. So 1 plus this guy. Okay? That's what you have down there. Follow that very carefully. 1 plus the product of this and this as it is. So when you begin to see complex things, you see how we will easily amalgamate them together or reduce them. In my next video, what I will do will be, because I'm not sure I'll be able to finish everything today. In this video, we will look at block reduction rules. Okay, if you have very complex block diagrams or feedback or closed loop systems, how do you reduce them so that it is easy to find that transfer functions? We look at maybe about 10 or so, 11 rules, thereabouts. Okay, so this whole system now is reduced to this simple open loop system, as it were. Okay, where this feedback system is now represented by its transfer function. Inputs, transfer function acts on this input to give you an output. Okay, and remember that it's a negative feedback system. All right. Then we'll quickly define what the error ratio is. If we look at this here, okay, and we usually will define the error ratio as the ratio of the output signal to the, the ratio of the error signal to the feedback signal. That's the error ratio. Okay, so from the transfer function of the closed loop system, okay, we know that C of S according to equation 2, okay, let's quickly rush back to equation 2. So you see, according to equation 2 says your C of S is G of S, E of S, okay? According to that, if we are dealing with our error ratio now, from this transfer function here, if we plug in the value of C of S here, okay, we have G of S, E of S divided by R of S equals G of S all over this guy down here, the denominator. G of S is common on both sides, so they cancel themselves. And what you are left with is E of S over R of S. So the error ratio actually is a ratio of the error signal to the reference signal, not the feedback signal, as I said earlier. Error signal to the reference signal. And that expression is given like so. Okay, 1 all over 1 plus G of S, H of S. Of course, you know why this is 1. This G of S, if we divide both sides by G of S, this will go away and that will go away, and what will be left there will be 1. This is what we call the error ratio. Error ratio. Now, let's go ahead and find out very quickly what the transfer function is for a positive feedback system. So for a positive feedback system, you see that your sign in the comparator here is positive. Okay, so this is a positive comparator. All right, so R of S is coming in as positive. B of S, your feedback signal, is also coming in as positive. So your E of S will no longer be R of S minus B of S. It will now be E of S equals R of S plus B of S. So when you manipulate, when you go ahead to derive the equation as we've done, when you move this plus B to the other side of the equation, it becomes minus. So this expression, this closed loop system has the same transfer function, the same form of the transfer function as the negative feedback system. The difference is this, all right? So C of S over R of S is, okay, the forward loop forward transfer function G of S divided by 1. This time we alternate those signs. So since we have close there, this is now minus, all right? And then we find the product of these two guys. This is the transfer function of a positive feedback system, and it reduces to this, okay? The input comes into your control system, okay? And that transfer function acts on the R of S to give you C of S. Now, what if your transfer function, your feedback transfer function is unity? What if it has a value of 1? So for a unity feedback system, okay, and you see how we've expressed it, okay, from being of the H of S that is here, this is now 1. So whatever C of S is bringing, it will multiply it by 1. So it is as good as this H of S not being here, okay? Because H of S is now 1. 1 times C of S will still be C of S. So C of S coming in will still be the same C of S going out. There's no need to put this block here. This is just one continuous, okay? That's why you see that we've removed the H of S there because H of S is 1, okay? So for a negative feedback system with unity feedback transfer function, this is your transfer function. C of S over R of S is moving forward. The forward loop transfer function is G of S divided by 1 plus because this is minus, okay? Plus, remember we have a product of this and this, but this is now 1. So G of S times H of S. H of S is 1, so that's why it vanishes. So G of S over 1 plus G of S. This is the transfer function for a negative unity feedback system. If it's a positive unity feedback system, then this is positive. This will be the same form, just that this becomes what? Minus. Okay? Since that is positive plus, this becomes negative minus. And this is the transfer function for a positive unity feedback system. All right? Great. Now let's look at a case of having a multiple input, multiple output system, a MIMO and or a MIMO system. Okay, when we classified, we talked about CISO and MIMO. CISO is single input, single output, and that's what we've dealt with here. Okay, we have a single input system and a single output system, but again, it is a closed loop. So how about this way? We have multiple inputs, all right, and we have an output. Okay, multiple outputs. This is a MIMO closed loop system. All right. So how do we handle this? Okay. So in a case where this system is linear, right? Remember we said transfer functions, and once you are seeing R of S, E of S, G of S, it means that we've carried out Laplace transforms, right? And we do that with and G of S here is a transfer function. That's a transfer function. Excuse me. This is a transfer function, right? We do that with linear systems. Say transfer functions may, all right, only be found for systems that are linear and time invariant. Where they are non-linear, we have to linearize them. Okay? So when multiple inputs are present in a linear system like this, right, we apply the principle of superposition. Remember I was saying for the system to be linear, it must possess two properties. The property of superposition and the property of homogeneity. The property of superposition says that if you have two inputs, okay, to this system, right, the overall output is going to be an additive sum, a summation of the individual outputs of those inputs if they are acted alone on that system. So that's what we're going to apply in finding out the transfer function of the MIMO system. What we do is we will isolate one input, okay, and find its input independent of the other inputs, right? And then we take turns like that. So if there are three inputs, we'll find the output of the first input, then, of course, freezing the other two inputs. Then we move the second input and freeze the first and the third input and find the output of that second input. And then we freeze the first two inputs and find the output of the third input, all right? And the principle of superposition says that since these three inputs are coming into this system at the same time, then the output of this system will be a sum, an algebraic sum of their individual outputs. And that's what we're going to do. All right. This is a, a two input MIMO system that we have here. Okay. So what we're going to do is first we freeze R2 out. Okay. We assume that this guy is not here, that R2 makes no impact on the system. So R2 is 0, right? That means that whatever comes out of G of S is the same that goes, G1 of S is the same that goes into G2 of S. All right? And so there's no need for a comparator here. This same thing is a straight line. That's why we've done away with this. So the block diagram that represents that is this. Okay, R2 is now 0. So R1 comes here. There's a feedback signal that comes, gives us an error signal that goes into our G1 of S that feeds directly into G2 of S, right? And then that gives us the output. And we take a bit of that output into your feedback transfer function, and then we have our feedback signal that goes to the comparator at the entrance point. Okay. Now, so the transfer function is, this is a feedback system. We're going to use the same form as we had before. Okay, the forward loop transfer function is what stays as the numerator because we have these two guys in series. Okay, okay, and this one acts on what's coming into it. This one acts on what this is going on. So the overall effect is just by multiplying these two guys together. Okay, when we come to block diagram reduction rules, we look at all of that. So you see us now combining these two blocks into one unit, and we do that by multiplying G1 of S and G2 of S. Okay, so that's my forward loop transfer function up there. Okay, all over one, the sign here depends on, this is a negative feedback system, minus, so this would be plus. So 1 plus the forward loop transfer function, which is the product of these two guys, G1 of S, G2 of S, and the feedback transfer function, H of S. So this guy here now is our transfer function. So consequently, or therefore, your output C1 of S as a result of the input R1 of S is G1 of S, G2 of S, R1 of S. What I've done is to multiply both sides of this equation by R of S. So R1 of S vanishes from this side, leaving only C1 of S. And on the right-hand side, what you would have will now be what we had here before times R1 of S, right? And that's as we've expressed there. So this is the output of this system when the input is R1 of S. Great. Now, the next thing we do is to make R1 of S now to be 0. Okay? And then R2 of S now is your input. Now, what happens here is, since nothing comes here, the same signal that comes out of H of S is what goes into G of S, right? And so we can do away with this comparator and move, let this be a single line, okay? We can stretch this to be on this side, okay? And bring this down so that whatever comes out here just goes into G1 of S. So G2 of S is the only thing up here. What I mean is this, like so. So when we now make R1 of S 0, all right, you see now we have R2 of S, excuse me, as the input, okay? And then this goes into G2 of S. Now somebody might be saying, oh, this is very confusing. Follow me very carefully so that I'll explain. Okay, now originally, when you look at what we started with, where R2 is coming into this system, you have a plus and a plus, right? A plus and a plus. What happened? How come it is now, where am I? How come it's now a plus and a minus? What's going on here? Okay, so let's follow this, right? So follow me very, very carefully. R2 of S comes here, right? It moves in this direction. There is a comparator here. Something is coming to add or take away from R2 of S. We don't know yet. Okay, but R2 of S comes in, it goes through to G2 of S before it gets to this junction here, and that's your output, right? Now from this junction, a portion of this output is taken, okay, into H of S, which is your feedback transfer function, right? Acts on that, outputs its own value. Now this value comes to a comparator, a negative comparator, so it's coming in as minus. Usually what we would have done is to take it away from, subtract this value from R1 of S. And now R1 of S is 0. So when you take away from 0, you end up with a negative. So this is 0 minus this guy. So even though this guy is vanishing, this same input here, because nothing is affecting, nothing is changing its values, is the same going in here, right? But it's now negative. This G acts on that negative value. When it comes here, the signal coming through this line is negative. When it comes here, this sign will now become what? Negative. You are adding a negative, plus minus is minus. All right. That's why you see that in the way we have now expressed this block diagram when R1 of S is 0 is to still show that this here is negative. The original comparator for R1 of S existed between H of S and G1 of S, right? And this no longer is there. Okay. Great. So here's what we have, right? So this comes in. Since R1 of S is 0, it makes no impact on this. So this will just flow that way. Okay. And that's what we have. So with this, we can now find the transfer function that the output, I beg your pardon, this here should be C2, no longer C1. Give me a minute, let me correct that. This will be, where am I on my slides? This should be C2 of S. Great, excellent. Thank you. All right? So C2 of S. So the transfer function is C2 of S all over R2 of S equals the feedback system. So the forward loop transfer function is G2 of S. That's what will be the numerator, divided by 1. The sign here depends on what is here. This is negative, so this will be positive, plus the product of the forward transfer function G of S and the feedback transfer function. All right, since this goes directly into that, we can find this by taking the product of these two guys. So G2 of S times G1 of S H1 HS is the same thing as G1 of S G2S HS, as we found. Okay, so this is the transfer function. So what that means is that your second output R2 of S is, you multiply both sides by R2 of S, and then you have this guy G2 of S, R2 of S, all over this guy down here. Okay, so the overall response of this system to these two inputs by the principle of superposition is going to be the sum of the individual outputs that we got by applying those inputs individually. Okay, so C1 of S, we found it to be this G1S, G2S, R1S divided by 1 plus G1S, G2S, and HS, right? Plus the second output, right? C2 of S. And this is what we have here. G2 of S and R2 of S, all divided by 1 plus G1 of S, G2 of S, H2 of S. Okay, so when you look at these two guys, okay, something is common. G2 of S all over the whole denominator is the same in both of these terms. And so we can factorize it out. Okay, and that's what we've done here. That the overall output of a MIMO system, we factorize this out. G2 of S out all over this whole guy down here, 1 plus G1 of S, G2 of S, H2 H of S, right? Multiply. What is left when you take this out is G1 of S and R1 of S. And that's what you have left here. And what is left when you take this guy away is simply R2 of S. And this here will give you the transfer function of your multiple input, multiple output system. All right. So I believe that you should now know what transfer functions are, and you should be able to get the transfer function for a given control system. When we come in the next video, what we'll do is we will now look at how to reduce block diagrams. Okay, and we'll give you some rules. And when you practice and practice and practice, once you see a block diagram in your mind, you would know how to reduce the system, all right, to make it simpler, and so that you can simply look at it if it's a feedback system, right? And get the transfer function from it without having to derive it the way we did at the beginning. So thank you very much, and I will see you in the next video. God bless you.